Hello student. So, today we will discuss constraint optimization problem. So, in the previous classes, so we have discussed the unconstrained problem. So, we have discussed the necessary and sufficient condition for optimality of unconstrained optimization problem. So, as we have discussed that the necessary condition for optimality of an unconstrained problem is basically you are taking the derivative and that first derivative should be equal to 0, that is the necessary condition, and for the sufficient condition. So, we are calculating the higher order derivatives. In case of single variable, we have calculated the higher order derivative, suppose second order, third order, fourth order, higher order non-zero derivative. So, depending upon odd or even. So, if it is odd, then in that case that is an inflection point, but if it is even, so we will see the value of the derivative, higher order derivative. So, if it is positive, so then the solution whatever we have obtained, that is a minima, and if it is your negative, so in that case the solution is the point is your basically a maximum point. For multivariable problems, so we are getting Hessian matrix, that means the second derivative will be an Hessian matrix. Then we will basically evaluate whether the Hessian matrix is a positive definite matrix or negative definite matrix or neither positive nor negative. If it is positive definite, then it is a minimum point, and if it is a negative definite, then that is a maximum point. If it is neither positive nor negative, so in that case the solution whatever we have got, and that is neither a minima nor maxima. So, we have already discussed this thing, and now today we will discuss about constraint optimization problem. So, what is the sufficient necessary and sufficient condition for optimality of constraint optimization problem. So, a general formulation of an optimization problem, constraint problem, can be written like this. So, here the problem may be a maximization problem or minimization problem. So, I can write that it is a either minimization or maximization problem. So, minimization or maximization are fx. So, it is a multivariable problem. So, therefore, we have total n variable here. So, okay, x1, x2, x3 up to xn. Then the problem has two types of constraint here. So, the problem is subject to zjx equal to 0, where j is from 1 to m, that means total m numbers of equality constraints. So, this is an equality constraint that zjx equal to 0, and you have inequality constraint that is hkx is less than equal to 0. So, this is an inequality constraint, and suppose we have total n, so we have total n number of inequality constraint. But today we will only discuss the problem with equality constraint, and inequality constraint we will discuss in the next class. So, today's lecture is basically on constraint problem with equality constraint. So, the problem with, as I said that, so today we will discuss this problem, that problem with equality constraint. So, either the problem is a minimization or maximization problem. So, the function is given, and then subject to zjx equal to 0, that means we have equality constraint, and number of equality constraint are m, and number of variable is your n. Okay. So, now let us suppose this is a function f x. Okay. Suppose this is a function f x, and it is a two variable function. So, we have shown a two variable function, and this is the control lines, and suppose this is a minimization problem. So, we are minimizing this function. Okay. So, we are minimizing this function, and in that case this is the minimum point. So, this is the minimum point, and this is the solution of the unconstrained optimization problem. So, this is the minimum point of this particular function. So, if I apply the sufficient and necessary condition, so I will get this solution, and this is the minimum of this particular function. Now, if there is a constraint, suppose zx, that is a constraint. So, we have only one constraint I have considered. So, if there is a constraint zx, then what will happen, this gx equal to 0, what does it mean? That that the solution should be on this particular Gx line. So, the solution will be on this particular constraint, because this is a equality constraint. So, therefore, whatever earlier solution we have, that is not a your feasible solution, and that is basically in the infeasible region. So, any solution which is on this particular Gx line, that is the feasible solution, and other solution, whether it is in this side or in the other side, those solutions are not feasible, because that will violate this constraint Gx equal to 0. So, therefore, the solution must be on Gx equal to 0 line. So, now that is not the constraint, that is not the solution of your problem. So, maybe the new solution is somewhere here. So, this is the new solution which will be your the constraint solution, and that is somewhere here in this particular point. Now, let us see how we can find out the necessary and sufficient condition for optimality in case of constraint optimization problem with equality constraint. So, let us take the same example problem. So, only thing is that I am considering here two variable problem. So, just to introduce the concept. So, I have considered two variable, that means the function is f of x1 and x2 and subject to z x1 x2 equal to your 0, and this is the function. This is the function, if I plot it, this is the function f x, and this is basically the z equal to 0 line. Now, suppose the solution is somewhere here. So, if I take the total derivative of this function at x1 x2, and basically I would like to find out, because I am trying to find out the necessary and sufficient condition. So, at optimal point that is your x1 star and x2 star, and that the total derivative should be equal to 0. So, this derivative df, which is equal to del f by del x1 dx plus del f by del x2 dx2 is equal to 0 at that your optimal point. So, x1 star and x2 star. So, this will be equal to 0. Now, if x1 and x2 is the solution of this constraint. So, if x1 and x2 this point is the solution of this constraint optimization problem. So, in that case what happen? It has to satisfy the constraint z x1 x2 equal to 0. That means, if x1 star and x2 star is the solution of this particular problem, then this point should be on the constraint line. So, therefore, z x1 and x2 should be equal to your 0. Suppose this is the point, and this is the point, that is your x1 star and x2 star. Okay. So, x1 star and x2 star. Now, if we go for any variation of dx1 and dx2, then the variation is admissible only when that whatever new points you are getting. Suppose if I go, okay, suppose if I go along dx1, so this is your dx1 and this is your dx2, then this variation will be admissible only when whatever new points you are getting. So, this is the new points I am getting. At that point, the z should be equal to 0, z at that function value, that constraint value at that particular point should be equal to your 0. So, therefore, I can write that z x1 star plus dx1 and x2 star plus dx2, at that point the z should be equal to 0. So, this must be equal to that z at x1 star plus dx1, x2 star plus dx2 should be equal to 0. So, now I can expand this thing using Taylor series, I can expand it. So, if I expand it, then I am getting that z x1 star x2 star, then del g by del x1 dx1 plus del g by del x2 dx2, and this must be equal to 0 as z x1 and x2 star on the z line. So, therefore, this must be this is equal to 0, and I am getting that I am getting this part. Okay. So, I am getting this part, which is del g by del x1 dx1 plus del g by del x2 dx2, and this is equal to 0. And what is this? This is nothing but the total derivative of the constant function at optimal point. Okay. So, at basically x1 star x2 star. So, basically x1 star and x2 star. Okay. So, x2 star. So, from here I can write what is the value of dx2. So, I can express this in terms of dx2. So, dx2 is equal to del g by del x1 minus del g by del x1 divided by del g by del x2 dx1. So, what is what this relation this equation is giving? So, if I suppose say that dx is basically, if I want to change the value of x by dx1, the corresponding dx2 I can calculate using this equation, and that only the new point will be your admissible point. So, if I look at, suppose if I look at this point, so right now I am here, so I can go along along this direction or along other direction, but I cannot go along this direction. Suppose I cannot go along, suppose this is the direction D. So, I cannot go along the direction D, because if I go along that direction, that whatever new point you are getting, that will be in the infeasible region, that will not be in the constraint line. So, in that case that solution is an infeasible region. So, I can go along that line. So, therefore, that new point can be calculated using this relation, that is dx2 equal to minus del g by del x1 divided by del g by del x2 dx1. Okay. So, I am getting this relation, and now the optimality condition. So, this is the optimality condition, we got it from the necessary condition of optimality, that is the total derivative at the optimal point, that is x1 star and x2 star should be equal to your 0. So, this is the total derivative of the objective function, and if I replace dx2 using this equation, then I am getting the total derivative which is equal to del f by del x1 dx1 minus del f by del x2 into. So, I am putting this part. So, this part is coming from dx. So, that is negative of del g by del x1 divided by del g by del x2 dx1, and I can further simplify it, and I will be getting it del f by del x1 into del g by del x2 minus del f by del x2 into del g by del x1 into dx1 equal to 0, as dx1 is not 0. So, this portion should be equal to 0. So, therefore, so this is the necessary condition for optimality. So, the necessary condition for optimality is del f by del x1 into del g by del x2 minus del f by del x2 into del g by del x1 is equal to 0. So, this is the necessary condition for optimality for optimization problem with equality constraint. Okay. So, the necessary condition we have derived, but question is that now it is actually not convenient to use this necessary condition. Okay. So, let us see that how we can use this in a little bit convenient way for finding the optimal solution of a constraint problem having equality constraint. So, now we will discuss the Lagrange multiplier method. Okay. Here let us take the same problem with two variables, that is minimization or maximization of f x1 x2 subject to z x1 x2 equal to 0. And now we have already obtained the condition for optimality in case of a constraint optimization problem having equality constraint. So, the condition is del f by del x1 minus del f by del x2 into del g by del x1 divided by del g by del x2 equal to 0. So, this is the necessary condition, this is the necessary condition for optimality. So, this is the necessary condition for optimality. Now, if I simplify, I can rearrange these terms and I can write that del f by del x1 minus del f by del x2 divided by del g by del x2 into del g by del x1 equal to 0. Okay. So, now putting the lambda. So, lambda is known as Lagrange multiplier. We will discuss about the significance of lambda later on, but if I put the lambda which is equal to minus del f by del x2 and divided by del g by del x2. Okay. So, what does it mean? It is basically showing that how if suppose del g by del x, what is del g by del x? Del g by del x is basically the change in the constraint function. So, okay, del g by the gradient of your constraint function, how it is influencing the gradient of the objective function with respect to a particular variable. So, I can write that this is lambda and which is equal to minus del f by del x2 divided by del g by del x2. So, if I put it in this equation, so finally I am getting del f by del x1 plus lambda del g by del x1 equal to 0. Okay. So, I am getting this equation, and similarly I can also write this equation in terms of your x2 variable. So, in that case this is del f by del x2 plus lambda del g by del x2 equal to your 0, and basically also put that this has to be satisfied because this is an equality constraint. So, therefore, g x1 x2 must be equal to 0. So, I am also putting this thing and all together. So, I am getting all the necessary conditions for optimality. So, necessary condition for optimality I am getting del f by del x1 plus lambda del g by del x1 equal to 0, del f by del x2 plus lambda del g by del x2 equal to 0, and z x1 x2 equal to 0. So, if I solve these three equations, now there are three variables here, that is one is your x1, x2 and lambda. So, and I am having and I have three equations. So, therefore, I can solve these three equations and I can find out the value of x1, x2 and x3, and whatever sorry x1, x2 and lambda, and whatever solution you are getting, that will be the stationary point of this particular your function. Okay. So, I can find out that one. Now, I can also define a Lagrange function which is basically L. So, L is a function of now three variables that is x1, x2 and lambda, and which is equal to f of x1, x2 plus lambda z x1, x2. So, this function is known as Lagrange function. So, I can define this. Now, if I apply the necessary condition for optimality in on this particular function, so I can write it. So, what is the necessary condition? That is the partial derivative with respect to your x1, x2 and lambda should be equal to 0. So, if I do that, so I am getting del L by del x1 equal to del F by del x1 plus lambda del g by del x1. You please recall that one, the previous slide. So, we also got the same your equation. So, but here we are finding it from the Lagrange function. Similarly, I can also take the derivative with respect to x2. I can write del L by del x2 which is equal to del F by del x2 plus lambda del g by del x2 equal to 0. And if you take derivative with respect to lambda, so in that case, so you are getting z x1 x2 equal to 0. Okay. So, we are getting all these three equations, and these are the necessary condition for optimality in case of constraint optimization problem having equality constraint. Okay. So, I got it, and now if I solve this three equation, so I can find out what is the value of x1 star, x2 star and your lambda star. Now, let us see the Lagrange multiplier method for general problem. So, suppose I have n variable here. So, I have total n variable and we have total m constraint. So, m variable, m constraint. So, in that case, so I can write the Lagrange function like this. So, now Lagrange function is x1, x2 up to xn, then I have total m constraints. So, therefore, lambda 1, lambda 2, lambda 3 up to lambda m, and this is equal to f x, then lambda 1 g 1 plus lambda 2 g 2, then plus your lambda m z m. Okay. So, you are getting this Lagrange function. Now, you apply the necessary and sufficient condition on this Lagrange function, and you can find out the value of x 1, x 2 up to x n, and you can also find out the value of lambda 1, lambda 2 up to lambda m. So, the necessary conditions are, that is del L by del x I, the partial derivative with respect to the variable. So, I have total n variables. So, I will get n equation. So, del L by del x I, which is equal to del f by del x I plus. So, now total constraints are m. So, it is a summation of j equal to 1 to m lambda j del g j by del x I. So, this is with respect to derivative with respect to x I, and then derivative with respect to lambda, that is your del L by del lambda j, which is equal to z j x equal to 0. So, how many equations we are getting? So, we are getting total n equation. Okay. So, n equation we are getting, and here we are getting total m equation. Okay. So, m equation we are getting. So, total equation. So, therefore, the total equation we are getting that is n plus m. Okay. So, n plus m. So, this much equation we are getting. Okay. So, now you have to solve this equation to find out the value of x 1, x 2 up to x n and lambda 1, lambda 2 up to lambda m. So, you can solve this and you can find out the solution, and that is basically you are getting the stationary point. Now, let us see that we have an equality constraint. Now, what will happen if I change the equality constraint, or basically we can relax the constraint, or we are tightening the constraint, then how basically it is influencing the optimal solution. Okay. So, that also we can evaluate, or that we can find out. So, let us see here. So, this is a minimization or maximization problem. So, this is min max f x, and here we have total n variable, and subject to that z x equal to b. Okay. I can write this b minus z x equal to 0. So, b is the right hand side of the equality constraint, that means suppose z equal to some value. Okay. So, I can write it b minus z x equal to 0. So, applying the necessary condition. So, if I apply the necessary condition here, necessary condition is that the partial derivative with respect to the variable should be equal to 0. If you apply the necessary condition, then I am getting del f by del x I minus, so minus lambda del g by del x I equal to 0, and here I equal to 1, 2, 3 up to n, and I am also getting that that b minus z is equal to 0. So, I am not writing the x here. So, but this is g x. So, b minus x equal to 0. Now, from the first equation, so I can write that del g by del x I, which is equal to del f by del x I by lambda. So, I can from the first equation I can write that one. So, del g by del x I, which is equal to del f by del x I by lambda, or I can also write it something like that, this is 1 by lambda and this is del f by del x I. For I can also write that if there is a small change in dB, then so if I take the derivative of, so dB minus dz equal to 0. So, if I take the derivative of this constant function, and in that case, so dB which is equal to the dz is the total derivative of the constant function, and which is equal to I equal to 1 to n del g by del x I dx I. Okay. So, this is basically I can write, and if I write it, so what is the value of del g by del x I? So, del g by del x I already we have calculated. So, already we have calculated what is the del g by del x I, and if I put it, so del g by del x I is 1 by lambda, this is 1 by lambda del f by del x I dx I. So, now what is this? What is this value? So, this term is nothing but the total derivative of the objective function. So, this is the total derivative of the objective function, and therefore, I can write this term is equal to df. So, what finally we are getting? So, we are getting finally this equation, and this equation is telling that dB equal to df by lambda, or I can also write that lambda equal to df by dB. So, lambda equal to df by dB, or df equal to dB lambda dB, df equal to lambda dB. Now, there are total 3 conditions. The lambda may be greater than 0, lambda may be less than 0, and lambda is equal to 0. Now, we just see, if you look at this relation, that is df equal to lambda dB, what does it mean basically? So, lambda is telling that how sensitive this constraint is. So, if lambda is 0, that means it does not have any impact, that it does not have any impact if there is a small, or if there is some sense in the constraint, that is you are either relaxing that constraint or tightening that constraint, that will not impact the objective function value. But otherwise, if lambda is positive, if the suppose it is a minimization problem, and lambda is positive. So, in that case, if you tighten the constraint, then what will happen? There will be a marginal improvement in the objective function. So, marginal improvement will be there in the objective function if you tighten the constraint, that means dB is negative. So, dB is negative, lambda is positive. So, in that case what will happen? df is negative. So, what will happen, that whatever objective function value you have basically already obtained, now objective function value will reduce if you tighten the constraint. If lambda is positive and you are relaxing that constraint, so in that case what will happen? The objective function value will not improve, basically it will increase. So, in case of minimization problem, if lambda is positive and you are tightening the constraint, so in that case there will be a marginal improvement in the objective function value. Now, consider the lambda is negative. So, lambda is negative. So, in that case, if you are relaxing your constraint, that means del B is positive, So, in that case what will happen? There will be a marginal improvement of your objective function value. But in that case, if you are tightening that one, lambda is negative, and if you are tightening, that means del B is negative in that case. So, what will happen? There will be a the function value will increase. So, if you are relaxing if you are tightening your constraint, so in that case the function value will increase, but if you are relaxing, then function value will reduce, there will be a marginal improvement. And the last condition, that is that lambda is equal to 0. So, it does not matter actually whether you are relaxing or you are tightening your constraint, it does not have any influence on the objective function value. Okay. So, that is basically the significance of lambda you are getting. So, therefore, if lambda is very large, in that case you have to be very careful in implementing the solution, because if there is a small change in the constraint or if value, so then what will happen? There may be very large change in the objective function value. So, you have to be very careful if lambda value is large, but if lambda value is 0 or lambda value is very small, that means that constraint is not that significant. So, it will not have much influence on the objective function value. Now, let us solve one problem here. We have to find out the maximum of this particular function, find the maximum of the function, that is f equal to twice x1 plus x2 plus 10 subject to there is a constraint that g equal to x1 plus twice x2 square equal to 3 using Lagrange multiplier method, and also we have to find out what is the effect of changing the right hand side of the constraint on the optimum value of f. Okay. So, let us solve this problem. So, what I will do basically, so I will write the Lagrange function now. So, Lagrange function is x1, x2 and lambda, and which is equal to f of x 1 x 2 plus lambda z x 1 x 2. So, I can write it like this, that this is equal to twice x 1 plus x 2 plus 10 plus lambda 3 minus x 1 minus twice x 2 square. So, apply the necessary condition. So, the necessary condition is that del L by del x 1 equal to 0. So, what I will get, that 2 minus lambda equal to 0, and from here I can find out the lambda equal to 2, or I can say lambda star equal to 2. The next necessary condition is del L by del x 2 equal to 0, and I will get 1 minus 4 lambda x 2 equal to 0, and from here if I solve it for x 2, I will be getting 1 by twice lambda star, and which is equal to 1 by 8. The third equation is del L by del lambda equal to 0. So, what I am getting, that 3 minus x 1 minus twice x 2 square is equal to 0, and if I solve it for x 1, so I will be getting x 1 equal to 95 by 32, which is equal to 2.97. Okay. Whatever solution I am getting, that is x star, this is 2.97, then 1 by 8, and lambda I am getting your 2. So, this is the solution I am getting, and now apply the sufficient condition just to check whether this is a minima, maxima or a neither minima nor maxima. So, what I will do, I will calculate the Hessian matrix. Okay. So, I will calculate the Hessian matrix. So, in this case the Hessian matrix is coming 0 0 minus 1, then 0 minus 4 lambda minus 4 x 2 minus 1 minus 4 x 2 0. So, if you put the Hessian matrix at x star, so then what I am getting? I am getting this 0 0 minus 1 0 minus 8 minus 0.5 and minus 1 minus 0.5 and 0. The eigenvalues of this matrix is minus 6.2972. So, therefore, this is a negative definite matrix, and whatever solution you are getting, that is an maximum point. So, therefore, eigenvalue is your negative. So, the optimal solution whatever we have got, that is your maximum point. And if we calculate the function value, that is f x star that is equal to 16.07. Okay. Now, also we have to check, suppose if we change the value of dB, okay, value of B, then what will happen. So, there are two ways to do that. So, the next part of this question is that we have to evaluate that if there is a change in value of B, then what will happen. Now, what we can do basically for that. So, I can take a different value of B and I can solve this problem and just see whether how basically it is changing the how objective function value will be changed. Now, or we can do what? We can apply the relation already we have derived, that is your df is equal to lambda dB. Now, suppose case 1, okay, that dB is equal to -1, then what will happen, that df is equal to 2 into -1 and which is equal to -2, and so the new f star value, okay, so the new f star value will be that 16.07 minus 2, so we will be getting 14.07. Okay. So, what does it mean, that if you tighten that one, so in this case the lambda is positive, so lambda is positive, problem is maximization problem, it is a maximum value. So, what will happen if we tighten that one? So, if we tighten the constraint by 1 unit, then corresponding change in the objective function will be 2 unit. Okay. So, we are getting the new objective function value which is lower than that one, and now it is 14.07. Now, there is another case, if we consider case 2, that dB is positive, suppose 2 unit. So, in that case what will happen, that df which is equal to 2 into now 2, so that will be 4. Okay. So, the new f star will be now 16.07 plus 4. So, that is 20.07. So, in this case what is happening, as lambda is positive and if you relax the constraint, okay, so in that case the objective function value will improve. Okay. So, there will be marginal improvement in the objective function value, and from 16.07, so we are getting now 20. So, therefore, if you relax it by 2 unit, then corresponding improvement in the objective function value will be 4 unit and you are getting 20.07, and that is the new objective function value. And if you tighten it, then it will reduce, and this is 14 point, we will get 14.07. Okay. So, this is all about today. So, today we have discussed the constraint optimization problem with equality constraint. In the next class, we will discuss constraint optimization problem with inequality constraint. So, what is the necessary and sufficient conditions for optimality in case of the problem with inequality constraint. So, see you tomorrow.